Welcome to the last part of the tutorial. In this part, we are going to talk about verifiability. Verifiability means checking some predefined global constraints on the entire system in a privacy-preserving manner. So earlier on, we talked about confidentiality. In the confidentiality, we said we have a set of enterprises, a set of participants. They want to collaborate with each other, but they don't trust each other. And the goal was to ensure that the blockchain system guarantees that these enterprises do not see the data of each other. Basically, the blockchain system guarantees the confidentiality of enterprise data. But here, in verifiability, we want to go one step further. We want to ensure confidentiality, and then we want to enable different enterprises to verify some property on the data of other enterprises in a privacy-preserving manner. So we want to enable, for example, enterprise A to access the data of enterprise B in a privacy-preserving manner to verify some property, to verify some constraints, where here we mainly target some global constraints which are known by all these enterprises. So to motivate verifiability in this part of the talk, we mainly target one application, which is a crowd working application. So we are going to talk about crowd working application and basically the challenges that crowd working environments face, and then how blockchain systems, permissioned blockchain systems, can help us to resolve these challenges. Crowdworking platforms have grown in number, diversity, and adoption. And they are envisioned as key technological components of the future of work. In a crowdworking scenarios, the requester sends a request to the platform like Uber and Lyft, and the platform forwards the request to some of the workers. A worker might send a contribution to the platform, and the platform forwards the contribution to the requester. The requester sends the reward to the platform, and the platform sends the share of the worker to the worker. So as can be seen, the crowd-working platform is an online intermediary between requester and workers. These crowd-working environments, however, need to address several challenges. First, we need to guarantee the compliance of crowd-working platforms. For example, the Fair Labor Standards Act, or FLSA, says that the total work hours of a worker per week may not exceed 40 hours. So a crowd-working platform, needs to guarantee this regulation for all its workers. So if we have hundreds of workers, or in case of Uber or Lyft, if we have thousands of workers on a platform, we need to ensure that no worker works more than 40 hours per week. Another example is Assembly Bill 5 or AB 5 that entitles workers to greater labor protection, such as minimum wage laws or sick leaves or something like that, and which is recently overturned by CA Proposition 22 that imposes its own set of regulations. So we have these global regulations, and these platforms, these crowd-working platforms, need to guarantee all these regulations. And there are many of these type of regulations. The second challenge is the crowd-working environments are not that simple. In real world, we have like more than one platforms. Like we have Uber, we have Lyft, we have Curb, we have Wheel. And requesters usually send their requests to more than one of these platforms. So like most of us as requesters have like both Uber and Lyft on our cell phones. And on the other hand, workers also often work on several platforms. So a driver works for both Uber and Lyft. So it makes the situation very complicated. And finally, we want to preserve the privacy rights of participants. Basically, we want to ensure that no participant obtains or infers any information beyond what is strictly needed. So, for example, if a driver works for both Uber and Lyft, the driver doesn't want either of them know that she works for the other. Now it makes the problem very difficult. Why? Because on one hand, we want to enforce regulations. And to enforce regulations, we need to have some degree of transparency. For example, if we want to enforce that a worker works at most 40 hours a week, we need to know that, okay, this worker works like this week, this worker works 30 hours for Uber and 10 hours for Lyft. So as a result, the total is 40 hours. So this worker is fine. But on the other hand, we want to preserve privacy. The worker doesn't want others to know that, doesn't want the Lyft to know that the worker works for Uber or vice versa. So we want to basically we need to reconcile transparency with privacy, and this makes the problem more complicated. So if we want to summarize the problems that we have in such contexts, first, we want to guarantee the compliance of crowd-working platforms with regulations. Actually, in the currently there are some local or per platform regulation exist. For example, both Uber and Lyft have such local regulations. They don't allow a driver to work more than 12 hours a day. But a driver who works for both Uber and Lyft can drive 12 hours for Uber, switch the platform, and work 12 hours for Lyft the same day. So you see, these regulations are currently per platform, are local. There is no like such global regulations. The second problem is we want to have a transparent and privacy preserving regulation enforcement. We want to enforce these regulations such that the privacy of participants is preserved. And finally, we want to have collaboration among these independent and competing platforms. And why do we need such collaboration? for two reasons. First, to enforce global regulations, because as I said, if I have a regulation that says, like FLSA rule, that says a worker, a driver can work 40 hours a week, and the worker works for both Uber and Lyft, then the worker might want to work for Uber like 20 hours, for Lyft 20 hours, or work for Uber 10 hours, for Lyft 30 hours. And this is not determined beforehand. During the week, we can say. So whenever a task is coming and we want to assign this task to that worker, we want to ensure that are we allowed to assign this task to this worker? So we need some collaboration between these platforms to ensure that we are allowed to assign this task to this worker. And this should be in a privacy preserving manner. So this is one reason for collaboration. And the second reason for collaboration is we might have complex tasks that may need multiple collaborations. So an example of these tasks are like micro task platforms. So consider like an NLP task, a summarization task. A requester comes with a summarization task. A requester has a text, a long text, and wants like different, like maybe 10 different or 100 different workers to summarize this long text. So the requester might submit this text to like Amazon Mechanical Turk, Prolific, and I don't know, maybe Microworker. 3 different microtask platforms. From the requester point of view, it doesn't matter which worker from which platform sends basically a contribution for this task. What is important is this requester needs 100 different contribution or 100 different summary for this task. So unlike ride sharing, Uber and Lyft, where each task needs a single contribution, we might, in some like crowd working scenarios, we might have tasks that needs multiple basically answers, multiple contributions. So in such a scenario, these three crowd working platforms, these 3 microtask platforms, Amazon Turk, Prolific, and Microworker, need to talk to each other, need to collaborate with each other to basically to say, okay, Amazon Turk say, okay, I have a worker that wants to basically send a contribution. Then Prolific says, I have another worker. So we need to say, okay, this is the first worker, this is the second order worker, this is the third worker, until we reach the 100 workers. So we need 100 different contribution, and we need to have some ordering between these 100 contribution. And why we need that? Because we don't want to accept like the next one, the 101 contribution. So there is a need for collaboration among these platforms, and there is a need for ordering contributions to say that, okay, this is the requested number of contributions, and this is the ordering between them, and we don't accept more than this. And so for that, we need some type of consensus among these like platforms. So it is, again, this is another complexity of another complexity of the problem. So Separ is an example of system that tries to address this issue. So in Separ, which is a paper at this year, the goal is to enforce regulations on multi-platform crowdworking environments while preserving privacy. So Separ tries to introduce three main design dimensions. One is the type of regulations that it can support. One is the privacy guarantees that it gives to the participants. And one is the architecture of the system, that it could be fully centralized or partially centralized. So I am going to explain this and saying that, okay, how this is going to connect it to the blockchain system, and how does blockchain help us to basically realize these three goals. So in terms of regulation type, which is the first design space, so we can express regulation as SQL constraints over a virtual universal table. So we can say that, okay, a regulation is basically on like a worker, a platform, a requester. It has some like time cost. It takes like 3 hours. It needs a contribution that like the content of the contribution and so on. And each regulation has like some communication part, which is communication between participants, and it has also some basically content, the content of contribution, the content of the basically request that is needed for that regulation, and so on. And these regulations can be categorized according to their SQL expression. So if a regulation has no join operation, it is simple, and if it needs some join operation, it is complex. Similarly, we can have row only, aggregate only, and mix based on using of group by and having, or basically using aggregate functions. We have another basically way of categorizing regulations. So we say regulations are either enforceable or verifiable. A regulation is enforceable if it must always hold. So for example, a regulation that says a worker must work at most 40 hours a week, it is a regulation that is enforceable. It must always hold, the FLSA regulation, and it is like maximum work hours. But a regulation is verifiable if it must hold periodically. So if a regulation says a worker must work at least 10 hours a day, 10 hours a week, then you can check this regulation at the end of the week. So you cannot like come to the worker at the beginning of the week and say, okay, you should work 10 hours a week. So show me that, verify to me that you have worked 10 hours this week, because it is the beginning of the week. You need to wait till the end of the week, and then you can check whether this worker has worked 10 hours or not. So these type of regulations are verifiable. you can check this type of this type of regulation periodically at the end of each week or at the end of each month. So, and these are basically minimum work hours if this like type of maximum and minimum are basically enforceable and verifiable. So the second design space is privacy guarantees that the system basically provides us. So we have a threat model which is system dependent, and for example, a system could be honest but curious, or covert or malicious. And we have a privacy model. So privacy model in the vision that we have, the privacy model, we assume that it is pluggable, and we consider three disclosures. So participants in a system are either not involved in a task and have not received a task. Consider the Uber example. A driver might not be involved in a task and might not and also not receive the task. So we have some privacy. Basically, we have some disclosure to such participants. The second type is the participants or the workers and platforms that receive the task but are not involved in task. Like a driver who receives some task, who sees that okay, there is a traveler that needs to go somewhere, but the driver doesn't accept that task. So the driver learns something from, knows that there is a task here, there is a traveler that wants to go from some place to another place, so it learns something. So we have disclosures to the platform and workers that have received the task but that are not involved. And the third disclosures are to the participants that are directly involved in the task, and definitely they have received the task. So the driver who accepts the task. So this is the privacy guarantees. So basically, based on these three disclosures, we define the privacy model. And the part that is mostly related to basically blockchain part is the architectural choice. So when we talk about regulation system, we need to have basically talk about two main critical components. One is the regulation management, where we need to model and enforce the regulations. So we have these regulations. So we need to model them, we need to define them, and we need to model them in a way that is enforceable. And then we need some way of enforcing these regulations. And then the second component is global state management. So the global state of the system, since we said that these are global constraints, and these constraints need to be verified by the entire system, and the system has a global state, so this state needs to be stored. So the global state management is basically the task of storing and maintaining the global state of the system. So each of these two components, the regulation management and the global state management, can be implemented either as a centralized or a decentralized, basically in a centralized or in a decentralized manner. So if we implement in a centralized manner, then it is easier to rapid prototype. However, it is difficult to ensure fault tolerance. it is difficult to ensure guarantee privacy and trustworthiness. And if we implement them in a decentralized manner, then it is indeed more compatible with the multi-platform nature of the system that we have. But on the other hand, it results in more overhead and complex communication protocols among these participants. So with this vision, with these three design space that we had, now we want to define separ. Separ is basically like a point in this design space. So in separ, the focus is on the basically interaction and not the content. So if you remember the U table that we had earlier on, we had worker, platform, requesters, and time cost, and also contribution and so on. So in separ, the focus is on interaction between these worker, platform, requesters. So we don't care about the content of contribution. We don't care about the content of a request. So it doesn't mean that the content of a contribution is not important or the content of a request is not important. Separ is like, as I said, it's like a point in this design space, and it is like an early version of this vision. So yeah, for separ, we just focus on these like interactions. So in terms of regulation, separ supports simple mixed with aggregate basically regulations, and both enforceable and verifiable regulations can be supported by separ. So separ defines basically the privacy model. The threat model is covered, non-including adversaries. So covered means basically adversaries aim to infer anything that can be inferred from the execution sequence, and the adversary is able to deviate from the protocol if no other participant detects it. And why non-including? There are some scenarios that if the participants can collude with each other, and separ cannot support that, so that's why separ is basically covered non-colluding. But indeed, most colluding scenarios can be supported by separ as well. And then we have a basically privacy model based on those three disclosures. And finally, the architecture of separ is a hybrid architecture. So here is where we talk about blockchain. So we have a registration authority. So the registration authority is implemented as a centralized basically component. This registration authority registers participants and models the regulations and distribute some crypto materials to nodes. And we have a multi-platform infrastructure, which is a basically decentralized component, and it maintains the global state within a blockchain. And it needs some basically different type of consensus protocols for nodes within the same platform, nodes across platforms, and basically global consensus for all platforms. So let's see how we guarantee verifiability. So in separ, basically inspired by eCash systems, we implement enforceable and verifiable regulations by managing 2 budgets per participants. And these budgets are basically lightweight, single-use, and anonymous tokens. So let's assume we have a regulation that says each worker can work at most 40 hours a week. We have a registration authority that every week generates 40 tokens. And what are these tokens? These are lightweight, single-use, anonymous. So it generates 40 tokens for each worker, and basically distribute these tokens to all workers. So every week, each worker receives 40 tokens. And then the worker can consume these tokens during that period, during that week, when it wants to basically be involved in a task. So for every regulation, we can have such tokens. So we might have a regulation that says each worker can spend 5 hours on each platform. So the registration authority generates 5 tokens per pair of worker and platforms, and send that to both platform and worker. And then when there is a task, then both platform and worker need to consume their basically their corresponding tokens. So this is how it works. So we have these lightweight, single-use, and anonymous tokens. So this token-based system is the base of verifiability that we have. So we have, and it has 5 different functions. We have generate function that is initialize the budgets and refill them, and it is by the registration authority. We have a spend function that basically different participants can spend their tokens. We have a proof function. This proof is needed for verifiable regulations. You remember, verifiable regulations are the one that are like saying that a worker can work at least 10 hours. The worker needs to work at least 10 hours a week. So you need to prove that you have worked at least 10 hours. So you need this proof function to say that, okay, I have worked at least 10 hours, and these are the 10 tokens that I have used. And we have check and alert if something went wrong, or if there is some to report some malicious spending. So if we take a look at the Separ architecture, we can see that each platform is basically implemented as a permission blockchain. We have nodes where we implement on, like, let's assume there are 3f+1 nodes to ensure that even if we have f malicious failure, then as we have seen earlier, then we can guarantee safety and liveness. We can guarantee safety and liveness in asynchronous basically periods. And then we have a blockchain ledger that we're going to talk about later. And you see that basically each platform is like this. So we have blockchain ledger, which is replicated on every node, and we have maybe 3f+1 nodes. You might say that, okay, we might have like 2f+1 nodes on some platforms if the nodes follow crash failure mode. And we have the registration authority that registers participants and send them the request, the tokens, and so on. So this slide presents the execution sequence of SEPAR. So first of all, we have two different types of tasks, internal and cross-platform tasks. Internal means the requester sends its request to a single platform, and cross-platform task means the requester sends its request to multiple platforms. So in the initialization phase, the registration authority sends tokens to worker, requester, and platforms. Then we have publication, where the requester sends a task to the platform, to either a single or multiple platform, and the platform sends a submission transaction to the blockchain, again to either the single blockchain or all involved, to the blockchain of all involved platforms, depending on the task, either it's internal or cross-platform. And then platforms will inform workers that there is some task, so you can send your contribution. Workers send contribution intent messages to the platforms. Now platforms send claim transaction to the blockchain. Again, if it is internal transaction, the claim transaction will be appended to a single blockchain. If it is a cross-platform transaction, the claim transaction needs to be appended to all involved blockchains. And then once the claim transaction is committed to the blockchain, the platform sends requests for tokens, collects all tokens, sends requests for signatures, collects basically group signatures, and put all of them to a verification transaction, and basically post that verification transaction to the blockchain of all platforms. Note that this verification transaction needs to be appended to the blockchain of all platforms. Why? Because the goal of the verifiability is to enable all platforms to check whether these constraints, these regulations are basically satisfied or not. And these regulations are modeled using these tokens. And these tokens are within this verification transaction. So when we append this verification transaction to the blockchain of all platforms, from now every platform can check whether these tokens are consumed in a right way or not. So that's why verification transaction needs to be appended to the blockchain ledger of every platform. And then everyone can check that. And at the end, we have the execution where basically the exchange of contribution and reward between involved party is done. So the blockchain ledger, if you see the blockchain ledger, we can have like different platforms in different colors. Each platform has a task submission T, and then each task has maybe one, or like this task has 3 contributions, C1, C2, C3, and each task has a verification transaction. So task might be internal or might be cross-platform task. So this is a cross-platform task between these two platforms, and it needs a contribution and it needs a verification. So each task has a task submission, one or several contributions, and one verification. However, what is maintained on different platforms is a linear chain, including the internal tasks, internal transactions of each basically platform, the basically cross-platform transactions that the platform is involved in them, and all verification transactions of the system. So, for example, this yellow one maintains all these yellows, maintains all these 3 because it is involved in these, and maintains all these verification, all these V's. Why? Because it needs to be able to verify other transactions, other tokens, other transactions that are processed in the entire system. So we had this blockchain ledger. We had we need to talk about consensus. We have local consensus, which is pluggable and depends on the failure model of nodes. We have a cross-platform consensus, which is needed among the involved platform. And we have global consensus, which requires the participation of all platforms. So if you remember, we had three types of transactions: submission transaction, claim transaction, and verification transaction. And we had two types of tasks: internal task and cross-platform task. For a submission and claim transaction, if the task is internal, we need local consensus because it is within a platform. If a task is cross-platform, we need a cross-platform consensus among the involved platform. However, for verification transaction, independent of the type of the task, whether it is internal or cross-platform, we need global consensus. Why? Again, because we need to enable all platforms to verify that the tokens have been consumed in a right way. Why? Because tokens are the regulation. Tokens are basically the way we model the regulation. So the cross-platform consensus that is used by SEPAR is a Byzantine fault-tolerant protocol because we assume that platforms do not trust each other. And basically, since it is a Byzantine fault-tolerant protocol, we have like an square message passing in accept and commit phase. And in each phase, we need agreement from the local majority of all involved platforms. And what is the local majority? It is the required number of matching replies from nodes of a platform. If nodes of the platform are Byzantine nodes, then we require like 2f plus 1 out of 3f plus 1. If they are cache only, we need f plus 1 out of 2f plus 1. Similarly, for global consensus, which is needed for verification transactions of all tasks. Again, it is a Byzantine fault-tolerant protocols, again, because of the trust issue. And again, we need agreement from local majority of 2/3 of the platform. So it is, again, all-to-all communication, all-to-all communication. And the difference is in cross-platform consensus, we need agreement from all involved platforms because because there is a task, there is a transaction that is going to be appended to all involved platform, and the order is important for all of them. But here there is a verification that needs to be appended to all platforms, but the order on each single platform is not important. So we need local majority of 2/3, not all of the platforms. So if we receive local majority from, for example, 3 of these platforms, then it is enough. We don't need to wait for local majority of P1, P2, P3, and P4. If we receive local majority of 2/3 of them, we can assume that, okay, 2/3 of them agree with that and go to the next step. So one problem with SEPAR is it needs a centralized registration authority to basically model these tokens. So we are going to introduce Quorum, which is another like permission blockchain. It is not in the context of crowd working environment. It is more in the context of financial transaction, but it is basically used for verifiability, and it doesn't need that centralized modeling of tokens. So Quorum is a permission version of Ethereum. It has a shared blockchain where basically we have a single shared complete blockchain of transaction. So you remember in SEPAR, we different enterprises, different platforms maintain different different views of blockchain. So the blockchains of different platforms were different. But here we have a single shared complete blockchain, and this blockchain is validated by every node, and it maintains all public and private smart contracts, or basically public and private transactions. So we have two types of transactions, public and private, and all of them are maintained in these shared blockchains. So we have a network in the basically underlying network where these private smart contracts are basically transmitted point to point, and the relevant parties. So if we have some smart contract that is between like 2-3 nodes, 2-3 parties, only those 3 parties are involved in that smart contract, and then the hash of that basically smart contract, private contract, is stored on the shared blockchain. So we have a shared blockchain that includes public transactions or public smart contracts and hashes or encrypted private contracts. So everyone can see that there are some contracts that are encrypted, and only the nodes who are involved in that contract can decrypt the contract and basically execute the transaction. So in Quorum, verifiability is basically guarantees using zero knowledge proof. So we can say that Quorum enables transferring of digital asset on a distributed ledger without revealing information about the sender, receiver, and quantity of asset. So it uses zero knowledge proof, and it uses the same technique as Zcash. So if we assume that it's a transaction in Bitcoin, so if we have a transaction in Bitcoin, we know that okay, this is the input, and the input is it is signed by like Alice, or it is signed by like a public key, and there is a transaction by this input and output. This is the quantity of output, and again we have input and output for the second transaction, and this is going to be another address which is signed for Bob or Charlie. So these are different addresses and these are different quantities. But in Zcash, if we show that in a very simple way, we don't know the quantity and we don't know what are the addresses. So this is the way that it is privacy preserving manner. It is, but it is verifiable. We can verify that this transaction is correct. We want to conclude our verifiability discussion in this slide. We have introduced two techniques. One is token based, which is in SEPAR, used in SEPAR, and one is cryptographic techniques, basically zero knowledge proofs, which is used in Coro. There is actually another technique, secure multi-party computation, which is used on top of Hyperledger Fabric, which we haven't introduced in this part. Token-based techniques require a trusted centralized authority to generate tokens. But on the other hand, SEPAR doesn't need to replicate our transactions on every node, resulting in improved performance. Cryptographic techniques, on the other hand, are decentralized, and there is no need for a trusted entity. However, they have considerable overhead, and if the system has many local transactions, since we need to replicate all transactions, we need to replicate the entire ledger on every node using such techniques are not beneficial.